In the last lecture, we introduced the wave equation, which is a partial differential equation used to describe the motion of waves in everything from strings and the ocean to electromagnetic waves like light or sound waves. And we looked at one particular method of solving the wave equation, D'Alembert's solution, which describes the solution to the wave equation in terms of propagating waves moving in opposite directions. Now, D'Alembert's solution is a very specialized process that only really works if you're far enough away from the boundaries of a domain so that they have no effect on your solution. In this lecture and in the next lecture, we're going to introduce a much more general process for solving partial differential equations, like the wave equation, that can involve boundaries. Now, this method, which is called the method of separation of variables, is quite an involved process with lots of steps. We're actually going to take this lecture and the next lecture to get through them all. But each of those steps is very simple, and it uses a lot of the ideas that we've already seen in this course. So in these two lectures, we'll look at the method of separation of variables applied to the wave equation. And in the next lectures, we'll look at the method of separation of variables applied to the heat equation and other partial differential equations. So let's get started. We're going to start with example 1. And you see here I've got the wave equation. It looks like the wave equation that we saw in the last lecture, except in this case we're looking at a wave equation with c is equal to 1. That is, we're going to see that the wave speed is equal to 1. And we have a couple of pieces of information to get us started. We're told that the value of u at x is equal to 0 and x is equal to pi is equal to 0 for all values of t, time. And we're told something about the initial displacement and the initial velocity of our wave. Now, we can think about these conditions here as being an initial condition. That's the initial displacement and the initial velocity. And as a boundary condition. That's what the first piece of information is telling us. So let's have a think about what these mean. What we're going to do is imagine that we're looking at a string that's tied between 2 points. So kind of like a guitar string. So at any moment in time, the displacement of this string from 0 is going to be given by our value u, our variable u. And that's going to be a function of both time and space. So we could imagine this string as being deformed in the following way. And at any moment, the vertical displacement is going to be given by u of x and t. So x is the distance along the string, and t is the time. So again, we're thinking about u here as being the vertical displacement of a guitar string, and that vertical displacement is going to depend upon the position along the string and how much time has gone by. Now, we're told that at all time, at values of x is equal to 0 and at x is equal to pi, our displacement is 0. So what that means is that at this point here, which is x is equal to 0, at one end of the string, and at the other end of the string, x is equal to pi, the string is pi long, that the string is tied down. What that means is that there is no displacement at those two locations. The string cannot move up and down at those points. So those are boundary conditions. They tell us what the value of our variable u of x and t is at the points x is equal to 0 and x is equal to pi. And those are going to be really important in terms of fixing what our solution is going to look like. The other information that we're given is the initial displacement, that is the initial vertical kick and the initial velocity. So in this particular problem, we're setting the initial velocity to be 0, and we have some value for the initial displacement. So we've sort of plucked the string, and then we're letting it go, and we're asking what happens next. So that's what our setup is going to look like. What we're going to see is that the first step we're going to do is to transform this partial differential equation for a function u of x and t, so a function of two variables. We're going to transform it into two ordinary differential equations for functions of one variable. And we're going to do that using the method of separation of variables, as I'll describe now. So here's our key assumption that we're going to make. We're going to assume that my solution u of x and t can be written in the form a function of x times a function of t. So our function u of x and t, it depends upon both space x and time t. And I'm going to assume that the form of that is a function of x multiplied by a function of t. Now, not every function of x and t can be written like that. So this is really an assumption. It's a simplifying assumption. And we're going to have to see if it makes sense. So we're going to sort of make a guess that the solution is of this form, and then see what the consequences of that are. And if we get something that is nonsense, then we know that this was a bad guess. So what happens when I make that assumption? Well, let's see what happens to our partial differential equation. Let me write it down again. So here's my partial differential equation, the wave equation. D squared u dx squared is equal to d squared, t was on the left, d squared t squared is equal to d squared u dx squared. So that was for c is equal to 1. Where here u is a function of x and t, and we're making the assumption that this is actually a function of x multiplied by a function of t. So this is the key assumption upon which the whole rest of the method depends. Okay, so let's see what the consequences of that assumption are. What does it imply? Well, we're going to have to ask what happens to the partial derivatives. So du dt is going to be the partial derivative of f times g. But you notice here, f is a function of x only, so it's not affected by that partial derivative. And g is a function of t only, so the partial derivative becomes an ordinary derivative. So I've got f of x times the derivative of g, and I'm going to write that as f of x g prime. So prime here means the derivative with respect to its argument. So g is a function of t, so g prime is the derivative of g with respect to t. We can also do this for the second derivative, so I've got d squared u dt squared. Once again, that partial derivative with respect to t does not affect f of x. It's going to hit my dg dt and turn it into a d squared g dt squared. And again, I'm going to use the notation g double prime to mean the derivative, the second derivative of g with respect to its argument t. So you see what's happened here is that the partial derivatives, because of the assumption that I made, have turned into ordinary derivatives. Let's see the same thing for the partial derivative with respect to x. So I've got du dx is equal to f of x. This time I'm taking the derivative with respect to x, so it's going to be df dx multiplied by g of t. And again, I'm going to use the notation f prime x to indicate the derivative of f with respect to its argument, x. And likewise, the partial derivative of u twice with respect to x is going to be d squared f dx squared g of t, which we'll write as f double prime x g of t. So we haven't done anything too hard yet. All we've done is make an assumption of the form of u of x and t, that it's a function of f, function of x multiplied by a function of t, and then shown that when I take partial derivatives, they get turned into ordinary derivatives. So let's write down now what the form of my wave equation is. So this implies that my wave equation, let's call it equation star, my wave equation becomes f of x g double prime t is equal to f double prime x g of t. Okay, so now I've got my expression in terms of ordinary derivatives. The next step is what's going to allow me to separate these two pieces. So what I'm going to do is I'm going to gather all the t terms on the left, gather all the x terms on the right. So I'm just going to divide the left-hand side by f of x g of t, and I'm going to divide the right-hand side by f of x g of t. And you notice that there's an implicit assumption here that f of x is not equal to 0 and g of t is not equal to 0. And that's a perfectly reasonable assumption, because if f or g was equal to 0, then by my assumption that u was equal to f times g, I'd have u is equal to 0. In other words, the string is not actually moving at all. So what we've gotten here is that we've taken all the t terms to the left, all the x terms to the right. So you notice that all I've got here is, on the left-hand side, a function of t only. And on the right-hand side, I've got a function of x only. So I took my partial differential equation, gathered all the t terms to the left, so I've got a function of t only on the left, gathered all my x terms on the right, so I have a function of x only on the right. But these two things are equal to each other. A function of t is equal to a function of x. But x and t are completely independent variables. The only way that they can be equals to each other is if they're both equals to the constant function. So we can only have a function of t equals to a function of x if both of those are actually just equals to some constant. So we'll call that constant k. So let me run through that argument again. You notice that I've got here on the left-hand side only terms involving t. So the expression on the left can only involve t. And on the right-hand side, I had terms only involving x. So this is only a function of x. But this equation here, which is basically just my partial differential equation, this equation says that a function of t is equal to a function of x. For every value of x, there is a value of t corresponding to this. Now, the only way that that can be true is if actually these two don't depend upon x and t. In fact, they're equals to some constant function k. Now, we don't know what k is yet. In fact, we're going to have to make assumptions about the form of k to find solutions for f and g. But this key step now allows me to write down two different equations. One for g of t and one for f of x. So I've got g double prime of t over g of t is equal to k, which implies that g double prime of t is equal to k times g of t. And the second equation I have is f double prime of x over f of x is equal to k which implies that f double prime of x is equal to k f of x. So notice what I've done here is I've transformed a partial differential equation in terms of for a function of two variables into two ordinary differential equations. So I've gone from partial derivatives to ordinary derivatives. And we can use our techniques for solving ordinary differential equations now. So I can slightly rewrite those equations if I like. We'll call them equation 1 is the equation for f of x. So f of x, two derivatives, minus k f of x is equal to 0. And I've got equation 2, g double prime t minus k g of t is equal to 0. Now you can see that both of these are second order homogeneous ordinary differential equations, and we can figure out the initial conditions or boundary conditions for these two equations in order to solve them using our standard techniques for solving second order ordinary differential equations. Now what we're going to do is we're going to tackle equation number 1 first, the equation involving x. And the reason we're doing that is because the boundary conditions for x are quite simple. They're that the value of my function is 0 at x is equal to 0 and x is equal to pi. My string is tied down. Those are going to give me quite simple solutions for f of x. And then we're going to go back and tackle g of t. So we're going to figure out what g of t is after we've figured out what f of x is. And then the last step will just be to put those two pieces back together again. So again, we're going to tackle f of x first. We're going to find the solutions of equation 1 first, and we're going to spend the rest of this lecture doing that. And then in the next lecture, we'll look at the solutions to g of t. So thinking about f of x here, this equation number 1, to find the solution of this, I need to figure out what the right boundary conditions are, because this is a second order ordinary differential equation, and the solutions to this are going to depend upon the boundary conditions. And they're also going to depend upon the form of the equation here, exactly what the value of k is, as we'll see. So let's figure out the proper boundary conditions for f of x. What we're going to do is we're going to make use of the fact that our string, the displacement of the string at x is equal to 0, and the displacement of the string at x is equal to pi is equal to 0. So let's remember what our separation of variables assumption was. I have a function of x times a function of t, and I have a function of x times a function of t, and x is evaluated at 0 and at pi. So what I've got here is that by tying down the string at the two ends, I found that f0 times gt is equal to 0, and f pi times gt is equal to 0. So in both of these cases, I've got something times something is equal to 0, so one of those things has to be equals to 0. Something times something equals to 0, something times something equals to 0. Now we've already seen that g of t can't be 0, because if it was 0, then my solution u would be 0 for all values of t. So that implies that the other thing, f of 0 is equal to 0, and f of pi is equal to 0. So this is using the fact that g of t can't be equals to 0 for all values of t. So these two expressions here are our boundary conditions expressed in terms of the function f of x. They're boundary conditions because they refer to the boundary at x is equal to 0 and x is equals to pi. So let's have a think about what our ordinary differential equation is that we have to solve. It's d squared f dx squared minus k f of x is equal to 0, with the boundary conditions f at 0 is equal to f at pi is equal to 0. So this is a second order homogeneous differential equation. And we've seen that the solutions to second order ordinary differential equations depends on the value of k. So in fact what we're going to see is we're going to get three different kinds of solutions that are going to correspond to the cases of k is equal to 0, k is a positive number, and k is a negative number. So we'll call these cases 1, 2, and 3. And what we're going to see is that the case of k is equal to 0 is going to give me f of x is equal to a linear function. The case of f of k is positive is going to give me f of x is equal to exponentials. And the case of k negative is going to give me f of x is equal to sinusoidal functions, cosine and sine. So we're going to actually tackle each of those cases one at a time. K is equal to 0, k greater than 0, and k less than 0, and apply our boundary conditions to see if those solutions actually make sense. So we'll start off with the first case. K is equal to 0. So this is case 1. Our differential equation now is d squared f dx squared is equal to 0. So we can immediately integrate this twice. Integrate it once to get df dx is equal to a constant, and integrate it again to get f of x is equal to ax plus b. So this is a function that depends linearly on x. It's just a straight line. Now, a and b are our constants of integration. To figure out what those are, we're going to have to make use of our boundary conditions, f at 0 and f at pi. So let's substitute in x is equal to 0 and x is equal to pi. So f at 0, we're told, is equal to 0. Substituting in x is equal to 0 into our linear solution gives me b is equal to 0. Likewise, I can substitute in x is equal to pi. I know that the value of f at pi has to be equals to 0. So subbing that in is going to give me a times pi plus b is equal to 0. So it's going to give me pi times a, which again implies that a is equal to 0. So what we found here is that the only form of the solution when k is equal to 0 that satisfies the boundary conditions is f of x is equal to 0. So if f of x was equal to 0, it would imply that u of x and t, which is f of x times g of t, is also equals to 0. So our solution is 0 for all space and all time. We're going to call this the trivial solution. It's going to come up a few times. And basically what it's saying is that your assumption was wrong. If your answer is equal to 0, it means that the only way that it's going to work is if it's 0 everywhere. So what that's saying is that our assumption that k was equal to 0 here ended up giving me something that didn't make any sense. And we can see that by thinking about what the solution might look like. So if I was to sketch the string, Here's x is equal to 0. Here's x is equal to pi. A solution f of x is equal to ax plus b would look something like this. It's a straight line. But we know that the string has to be tied down at x is equal to 0 and x is equal to pi, which means that the only straight line that will connect those two is the straight line f of x is equal to 0. So f of x is equal to 0 is the only solution that satisfies the boundary conditions. We'll call them BCs for short, when k is equal to 0. So in other words, k is equal to 0 does not give us an interesting solution. So we need to look at one of the other cases. The next one we'll look at is k is a positive number. Now what I'm going to do here is I'm going to make a little trick here that will make my calculation slightly neater. So I'm going to set k is equal to p squared, and of course that is automatically going to give me a number that's positive as long as p is greater than 0. So I don't know what k is, but I want it to be a positive number, so I'm going to set it equals to p squared, and that's just going to give me a slightly neater calculation. So what does that say about p is greater than 0? I don't want p equals to 0 because that would give me k is equal to 0. So what does my differential equation become? I've got d squared f dx squared minus p squared, so k is equal to p squared, f of x is equal to 0. So we're going to assume a solution of the form f is equal to e to the lambda x. So every derivative of f becomes a power of lambda. So my characteristic equation is that. It's my characteristic equation, and it has the solutions lambda is equal to plus or minus p. So I know that then from our methods for solving ordinary differential equations, I know then that the solution will be of the form e to the plus px plus b e to the minus px. Okay, so we're back at the problem that I had before. I have unknown constants of integration a and b that I need to figure out by using my boundary conditions. So we're going to fix a and b using boundary conditions, BCs. So let's look at the first one. I know that at x is equal to 0, I have f at 0 is equal to 0. So let's substitute x is equal to 0 into the form of my solution. So I've got a e to the 0 is 1 plus b e to the 0 is 1. So that gives me that a is equal to minus b. I need a second piece of information to fix both a and b. So at x is equal to pi, again the string is tied down there, so f at pi will be 0. So substituting in x is equal to pi and also making use of the fact that a is equal to minus b is going to give me a times e to the p times pi minus a times e to the minus p times pi. So I substituted in x is equal to pi and b is equal to minus a. So I can take out the common factor of a, e to the p pi minus e to the minus p pi. So this is equal to 0. Our boundary condition is that this thing is equal to 0. So I've got something times something equals to 0. So I know that either this implies a is equal to 0 or e to the p pi minus e to the minus p pi is equal to 0. So let's consider the first possibility. A is equal to 0. Well, that would mean that, again, f of x, it would mean that b is also equals to 0, which implies that f of x, which was a e to the px, b e to the minus px, that would just give me f of x is equal to 0. So again, this is giving me the trivial solution. It's giving me a solution that's 0 everywhere. What about the other possibility, e to the p times pi minus e to the minus p times pi? Well, what I can do here is I can rearrange this equation slightly. E to the p pi equals e to the minus p pi. I can then multiply both sides by e to the p pi. Because, of course, e to the p pi is not equals to 0. And I have here e to the 2p pi is equal to 1. So e to the 0 is equal to 1, which should imply that p is equal to 0. But you remember that we explicitly stated that p couldn't be equals to 0. If p was equal to 0, I would just get back the case k is equal to 0. So we didn't want to include that possibility, so we excluded it here. So p was equal to something greater than 0. So what we've ended up with is a contradiction. We assumed that p was greater than 0. So let's review what we've done there. We've looked at two different possible values of k. I looked at k is equal to 0, and I looked at k was equal to a positive number, which I called p squared. And in both cases, I found the solution. The first was a linear solution, the other one was exponentials. So in both cases, I found the general form of the solution in terms of unknown coefficients a and b, a and b. And I fixed those coefficients using the boundary conditions. F at 0 is equal to 0 and f at pi is equal to 0. And I found in both cases that ended up giving me just the trivial solution. F of x is equal to 0 for every value of x. F of x is equal to 0 for every value of x, or it gave me a contradiction, that p is a number equals to 0. So what that's telling us is that k is equal to 0 and k is a positive number does not give me an interesting solution, a non-trivial solution to this differential equation. So I'm going to have to look at the third case, k is equal to minus p, a negative number. So I'm going to use a very similar trick to the last case. Looking at k is equal to a negative number, I'm going to set it equals to minus p squared. So again, I'm doing this and making sure that p is not equals to 0 because it's going to simplify my calculation. You can see k is equal to minus p squared is always going to give me a negative number. So let's take a look at what our differential equation becomes. I've got d squared f dx squared plus p squared f of x. Let's assume solutions of the form f of x is equal to e to the lambda x, which is going to transform every derivative with respect to x into a power of lambda. So I have the following characteristic equation, which has solutions lambda is equal to plus or minus I times p. So I've got complex roots to that characteristic equation, which of course gives me a combination of sines and cosines. So it's given me sinusoids. So the case of k is a negative number ends up giving me complex eigenvalues, lambda, and it ends up giving me sinusoidal type solutions. Once again, I have unknown integration coefficients that I'm going to fix using the boundary conditions. So we have f at x is equal to 0. I've got f at 0 is equal to 0. So that's going to give me a times cosine of 0, which is 1, plus b times 0. So I just end up with a, and that's going to give me that a is equal to 0. So it kills off the term involving cosine. And at x is equal to pi, I also have f is equal to 0. So we know that a is equal to 0. That just leaves me with b sine px. So I forgot my px here. Okay. So what I found here is that I have b times sine px is equal to 0. Something times something equals to 0, which means that one of those things has to be 0. So there's two possibilities. Either b is 0 or sine px is equal to 0. Now, if b was equal to 0, it would imply that f of x, which is a times cosine px plus b times sine px, is equal to 0, which would imply that u of x and t is equal to 0, which is the trivial solution again. So b cannot be equals to 0. It leaves me with the other possibility that sine px is equal to 0. Excuse me, sine p pi. So just moving back a line here, we wanted to put in x is equal to pi, so that's x is equal to pi. F at pi is equal to b sine pi. There we go. So that was an error as well here. B sine p pi, and this is sine p pi. There we go. So sine p pi is equal to 0. Now remember, p can't be equals to 0, so that means that I need to think about what possible values I could put in for p there to guarantee that I get 0. Well, we know that sine of any integer is equal to 0. So this will be satisfied, or is true, if p is equal to any integer, 1, 2, 3, 4, 5, any integer at all. So we're going to say let p equals to n, where n is a number 1, 2, 3, and so on. So it's one of the counting numbers. So in our third case here, we looked at negative, k is a negative number, which we said was negative p squared. Our solution then was of the form of a sinusoidal solution. And when I used my boundary conditions, I ended up finding that the only possible non-trivial solution, that is when I don't have just this whole thing equals to 0, is going to happen when I have a solution of the form f of x is equal to b times sine nx. So that's the only solution that is non-trivial. Now thinking about this a little bit, we can see how this makes sense, because again we've got those boundary conditions and I somehow have to squeeze in an f of x is equal to a cosine px plus b sine px. So I need to figure out the a's, the b's, and the p's that will fit in to my domain here. So x is equal to 0 to x is equal to pi. And the only constraint I have is that I have to have 0 at x is equal to 0 and x is equal to pi. Well, what kind of sinusoids would fit in there? Well, I could have sine of pi x, sine of x. I could have sine of 2x, so that's sine x. I could have sine 2x. Let's use a different color for that one. I could have sine of 3x. And so on. I can keep on adding in any integer multiple of x, sine integer times x. So I could even have sine 4x and so on. So what we found here is that the solution that is a sinusoid and fits in with a value equals to 0 at x is equal to 0 and x is equal to pi is any integer multiple of x. So b sine nx. Sine x, sine 2x, sine 3x, sine 4x, and so on. So in fact what I've done is I found infinitely many solutions. A solution for every one of the counting numbers, n equals to 1, n equals to 2, n equals to 3. So what I'm going to do is I'm actually going to indicate that by putting a little subscript n here beside my f and my b. And the reason I'm doing that is because this solution is for n is equal to whatever, 1. And so I'm going to have a different form of my solution, fn, and I'm going to have a different constant multiplying it in front, bn. So that is now the solution for the spatial part, the x-dependent part of my partial differential equation. Remembering that the full solution is actually going to be the product of f of x and g of t, and we have found infinitely many solutions for f of x. So we found f1 of x, f2 of x, we're labeling them fn of x for n is equal to 1, 2, 3, and so on. Any one of those would satisfy that wave equation. We have yet to find what g of t is, and that's what we're going to tackle in the next lecture.